So you are welcome to today's class. Today you are going to learn how to draw the structures of your carbohydrates, starting from monosaccharide, disaccharide, polysaccharide in an easy peasy way. Trust me. But before I start, I would like to introduce you to certain things like what is carbohydrates. So how do we define carbohydrates? Carbohydrates are basically what? Alkana or what? Ketones. It means that what? They have this carbonyl functional group. So carbohydrates, all carbohydrates are either what? Alkana or what? Ketones. It means that what? They have this carbonyl functional group. I hope that is clear. Don't forget that what? For alkana, this functional group is at the end of the chain. While for ketones, this carbonyl group is at the what? Middle of the chain. That is for alkana, we are going to have something like this: carbon, 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 and the functional group will be at the end of the chain. Okay, this is what? Alkana. But for ketones, the functional group will be somewhere in between the chain. One, so it can be what? Here. So carbohydrates are either what? Alkanas or what? Ketones. But that is not all. They are what? Alkana or ketones that has polyhydroxyl group. That is, they have a lot of what? OH group. I hope that is clear. So let me just bring a particular example here. Me having 3 carbon. Okay, the first thing is to draw the functional group. Carbohydrates have what? Carbonyl functional group. So this is the functional group, and alkana. And they also have what? Polyhydroxyl group. It means that, okay, I have to what? Put an OH here. But I won't stop here. Why? Because this is just a single OH. This is not poly OH. This is just a single OH. It means that what? I need to what? Add one more OH. So this is what? Another OH. So this is poly now. Poly from 2 upward. That is to tell you that the smallest carbohydrate has how many carbon? 1, 2, 3. It has what? 3 carbon. And you understand why? Because of this polyhydroxyl. I hope that is clear. And also, another thing I would like to introduce you to is what we call chiral carbon. What is a chiral carbon? A chiral carbon is a carbon that has 4 different groups attached to it. It has what? 4 different groups attached to it. Let's look at it. This is a carbon. Okay. It then has what? 4 different groups attached to it. OH, hydroxyl, hydrogen attached, fluorine attached, and what? Chlorine attached. So this type of carbon is a what? A chiral carbon. Why? Because it has 4 different groups attached to it, which are hydroxyl, chlorine, hydrogen, and what? Fluorine. I hope that is clear. And one thing about chiral carbon is that what? They do what? They do flip. They can form what? Mirror images. So if I should place this in front of a mirror, what is going to happen? The OH and the hydrogen here are going to what? Flip. Why? This chlorine and the fluorine are not going to what? Flip. Because mirror does not do what? Vertical rotation. Mirrors only do what? Lateral rotation. I hope that is clear. So don't forget, we said chiral carbons should have what? 4 different groups attached to them. So is this a chiral carbon? Yes, this is a chiral carbon. It has 4 different groups, which are hydroxyl, fluorine, hydrogen, and chlorine. So this is what? A chiral carbon. What about this? This is not a chiral carbon because it has what? 3 groups attached to it. And a chiral carbon should have how many groups? 4 groups. And the 4 groups should be what? Different. What about this? This is also not a chiral carbon. Why? Because it has what? 2 groups that are what? The same, which are this what? Hydrogen and hydrogen. Though it has 4 groups are attached to it, but all the 4 groups are not what? Different. This hydrogen and hydrogen looks alike. So this also is not a what? Chiral carbon. So this is the only what? Chiral carbon. And one thing again about chiral carbon is that what? Chiral carbon do form mirror images. They do form mirror images. Okay. So if this is the mirror, and don't forget one thing about mirror is that what? Mirror does what? Lateral rotation. Mirrors will not do what? Vertical rotation. They only do what? Lateral rotation. So it means that what? It is only this OH and this H that will be what? Flipped in the mirror. So we are going to have something like this in the mirror. chlorine. Why the OH will now be here now? Okay, the hydrogen will be here and the Cl will be what here. So only these two guys will be what? Will be flipped. I hope that is clear. So let me just bring a random compound, and we are going to determine the amount, that is the numbers of chiral carbon we have in that compound. Okay, so let me just think about a 5 carbon compound, like having 1, 2, 3, 4. Let me put the 5th carbon here, 5. So don't forget, for what is it called, carbohydrates, right? The first thing we have to do is to what? Put the functional group. So if this is what an alkyl carbohydrate, I have to put my functional group what? Here. And the next thing I will do is that what? I will turn this into a box. So I've already what? Put something here. So I will then go down to the bottom of the chain to put something there so that I can have it like a box. Like I'm covering the whole chain now. I have something at the top. So let me put something at the what? At the bottom. And what do you think will be at the bottom? It is hydroxyl. I'm going to add an hydroxyl here. Why? Because we said what? After our functional group, the rest of the carbon will be what? Filled with what? OH. So I'm going to have OH here. Hydrogen and hydrogen. You can see that what? I've already created a cover like this. Something is at the top while something is at the bottom. So I can then fill with what? OH. But I just want to create a random stuff. So now let us count. How many chiral carbon do you think we have here? Is this first carbon a chiral carbon? No, it is not a chiral carbon. And why? Because it has 3 groups attached to it. It has oxygen, hydrogen, and everything at the bottom here attached to it. Is that clear? So this is not a chiral carbon. What about the second carbon? Is this a chiral carbon? Yes, it is a chiral carbon. How did I know? It has OH attached to it here. It has hydrogen attached to it here. It has everything at the top here attached to it, and it has everything at the bottom here attached to it. So these guys are all what? Different. So this is what? A chiral carbon. What about the carbon 3, the third carbon? Is it a chiral carbon? Let's check. It has OH attached to it. Okay, it has hydrogen attached to it. It has everything here attached to it, and it also has everything here attached to it. All what we have here are different from all what we have here. Hydrogen is also different from what? Hydroxyl. So this is also a what? A chiral carbon. What about the third guy? It is also a chiral carbon. Okay, it is also a chiral carbon. OH, hydrogen, what we have here, and everything at the top here. So this guy is also a what? Chiral carbon. What about this third guy? It is not a what? A chiral carbon. Why? Because it has what? 2 hydrogens. I hope you understand that. So it has one group, third, and the what? Last, everything up here. But these 2 guys are what? The same thing. And a chiral carbon should have what? 4 different things attached to it. I hope that is clear. So it means that what? This random guy has how many stuff? How many chiral carbons? Just 3 chiral carbons. Carbon 1, carbon 2, and carbon 3. But you know that what? This guy can also form a mirror image. Don't forget that we said chiral carbons do form mirror image. So let us form this guy mirror image. So don't forget we said chiral carbons do form mirror images. So we have how many carbons there? 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Okay, but do you think this guy is going to flip here? No, this one is not going to flip, because number 1, this one is not a what? A chiral carbon. You understand that, right? So I'm going to have this one as this. I hope that is clear. What about this carbon 2? It is a chiral carbon, so it is going to flip. So the OH will come here, OH and hydrogen. What about the third one? It is what? A chiral carbon. The OH that is here is going to move here while the hydrogen will turn. Okay, so the OH will what? Move here while the hydrogen will what? Come here. What about the fourth one? Yes, it is a chiral carbon, so the OH will come here and the hydrogen will be here. I hope it is clear. What about this last guy? It is not a chiral carbon, right? Due to these 2 hydrogen. So it means that what? This one will not flip. Because we said only chiral carbons what? Form mirror images. So all this one will still be as they are before. So you notice that what? These 2 guys are what? The same thing. So how are we going to name them? And don't forget, I said these 2 guys are what we call what? enantiomers. Enantiomers are what? Isomers that they are what? Mirror images of each other. This one is the mirror image of this. Why this one is also the what? The mirror image of what? Of this. So how are we going to differentiate them? This is where the idea of B and L comes in. I hope you understand that. So this is a random compound, that is a random carbohydrate. So let me just give it a random name. Like, let me call this AB because they are the same. I will call this AB. I will also call this one what? AB. But what type of AB? What type of AB is this? What type of AB is this? We have to differentiate. So we do use one thing, which is what? So what we do use is that what? We do look at the what? The last chiral carbon. When you look at this one, this is the first chiral carbon, this is the second chiral carbon, this is the third chiral carbon. Why this is not a chiral carbon, right? Because of this, it means that what? This carbon 4 is the what? The last chiral carbon. Okay, so we are going to look at the position of the OH on the last chiral carbon. We notice that what? Okay, for this one, the OH is on the right. It means that what? This one is what? A D carbohydrate. Look at this one. This is not a chiral carbon. This is the chiral carbon, a chiral carbon, and this is the last chiral carbon. This one is not a chiral carbon, right? So on this chiral carbon, the OH is on the what? On the left. So we call this one what? L carbohydrates. Let me just call them L carbohydrates. Why this one is called what? A D carbohydrate. I hope it is clear. So now the question is, why do you think we choose the last chiral carbon? The last chiral carbon is the what? The chiral carbon that is what? Far. It is very far from the what? From the functional group. The last chiral carbon is the what? The farthest chiral carbon from the what? Functional group. So let us pick it. Okay? We don't want to pick the one that is close to the what? Carbonyl. That is we don't want to pick the chiral carbon that is close to the functional group. So we pick the last one that is close, the farthest one from the what? Functional group. And I hope you understand that. But don't forget, this is not a what? Chiral carbon. So in any structure you see, just look at the last chiral carbon. If you notice that, okay, the last chiral carbon, the OH on it is on the right hand side, you will know that what? Okay, this is a D carbohydrate. And if the OH is on the other side, you will know that what? This is what? L carbohydrates. Thank you. Let's move into the structures of our monosaccharide. Okay, we have different types of monosaccharide depending on the numbers of carbon. Okay, we have the what? The 6 carbon monosaccharide. And the 6 carbon monosaccharide are what? Glucose, galactose, mannose, and fructose. Don't forget that we said our carbohydrates are either what? Alkana or ketones. Okay, carbohydrates that has the alkana functional group are known as what? Aldoses. Okay, why those ones that has the ketone functional group, that is if the functional group is found somewhere in between the chain, those ones are known as what? Ketoses. Okay, so now we have glucose, galactose, and mannose with fructose. All these 4 guys are what? Monosaccharide with what? 6 carbons. Okay, but the glucose, galactose, and mannose, they are all what? Aldoses. Okay, because they have the carbonyl, because they have the alkana functional group, they have their functional group at the end of the chain. Why fructose is a what? Why fructose is what? A ketose. Okay, just take this fructose as a fruit here. So I don't think we should add a fruit among these things. So the fruit here is the only what? Odd one. So it is what? A ketose. Don't forget that what? The fruit is what? Is sweet. So, and kissing also is what? Is also sweet. So we say fructose is what? A ketose is kissing. Okay, so now those are what? 5 carbon monosaccharide. We also have those are what? 6 carbon monosaccharide. We also have the 5 carbon monosaccharide, 4 carbon monosaccharide, and 3 carbon monosaccharide. Don't forget, we cannot have a 2 carbon monosaccharide, and I showed you why. Because if we should have 2 carbon monosaccharide after the functional group and we then have 1 more carbon, we are not going to get polyhydroxyl, right? So the least saccharide, that is the least carbohydrate, has what? 3 carbons. So how do you remember all the monosaccharide that have what? 5 carbons, those that has 4 carbons, and those that has 3 carbons? You can use this short cut, which is what? red BC, that is your red blood cell. And we are going to label them from 5, 4, 3, 2, 1. The 5, which is this red, it has 5 under it. I've been on 5, 4, 3, 2, 1. I hope you understand that. So this R is for what? Ribose. Okay? Now, immediately after ribose, the next thing that should come to your mind is what? Deoxyribose. A ribose in which oxygen has been removed from its deoxy. I hope it is clear. So after ribose, we have deoxyribose. We also have something called what? The ribulose. We also have what? Arabinose. You notice that what? All of them have what? R. Okay? While the last one here, we have the what? The xylose. And then lysose. You notice that what? This xylose and lysose have the same letters in their spelling. They just rearrange it in order to just give this one another name. Okay? So the 5 carbons are what? Ribose, deoxyribose, ribulose, arabinose, xylose, and lysose. Now, all these guys that we have here are what? All aldoses. They all have the alkyl functional group except this ribulose. So why? Because of this U in the center. So when you see ribose, okay, ribose is alkyl. What about ribulose? The U is just like me telling you that okay, it has the way in the middle. So we have U, and you see the U here also for erythrulose. So it is only ribulose that is what? A ketose here. I hope it is clear. It is only ribulose that is what? A ketose. Now let us move to the E, which is erythrose, okay, and erythrulose. So all these two guys have what? 4 carbons. Erythrose is what? An aldose. Why? Erythrulose. This U is just like the carbon, the functional group going inside, but somewhere in the center. Okay? So this is erythrulose. And the last one, and the erythrulose is what? A ketose. The last one that I have here is what? Dihydroxyl what? Acetone. I hope that is clear. And we also have what? Glyceraldehyde. Okay? I hope that is clear. Now let us move into how to draw discussions. Don't forget the red BC, that is your red blood cell, the red BC, and you can get our different stuffs from here. So how do we draw the structures of our carbohydrates? So now let us move into the what? Structural aspect. How do we draw the structures? For us to draw the structures of all our monosaccharides, we need to divide them into 2. The real guys and what? Others. Okay? What are the real? The real is for the what? Ribose, deoxyribose, and ribulose. That is for the R. The E is for what? Erythrose and erythrulose. The A is for the what? Arabinose, and the L is for the what? Lysose. While others like glucose, galactose, they follow another what? Pattern. Now let us look at this real pattern. Starting from this E. Now look at E. When you look at the structure of your E, the way we do write our E, you write it as what? A straight line, that is a vertical line, then what? 3 what? Horizontal lines. So you notice I wrote this vertical line with what? A red marker. This vertical line will serve as the what? The carbon chain. Okay? Why these black lines will serve as the what? OH. It means that if I want to draw the structure of erythrose or erythrulose, I will draw it in form of E, and all the OH will be on the what? Right hand side, just like this E. For R, which is for ribose, deoxyribose, and ribulose, the red marker is the what? The vertical line is the red marker, which will serve as the what? The carbon chain. And completing your R, you will notice that what? It is what? On the right hand side. It means that what? All the OH hydroxyl will also be on the what? Right hand side. The next one is the what? Arabinose, which is the A. Arabinose is spelled as what? A and R, right? So for the R, we have the vertical line and this thing that looks like a 2 to complete your R. That is to tell us that what? Our OH will be on the what? Right hand side. But we also have A on the what? This left hand side. It means that what? Most of the OH, that is hydroxyl, will be on the what? Right hand side, and just a single hydroxyl, this is A. Just one of the hydroxyl will be on the what? Left hand side. And because it is A is also the same thing as what? First letter. It means that what? The hydroxyl here will be on the what? The hydroxyl on the left side will be on the what? First chiral carbon. I did not say first carbon. I said what? First chiral carbon. Now, the next one, which is the lysose. All you just have to do is to just what? After drawing the carbon chain, which is this L, just which is this vertical red line, just draw the what letter L on it. I hope that is clear. So what is it called? For the alkanas, that is the aldoses, do you know how you are going to cover your chain? The first thing you have to do is, okay, let us move to the structures of the erythrols. Okay, but one thing about the structures of this real and others, all of them, after drawing the what your carbon chain, like let's take for instance your carbon chain, 1 2 3 4 5. The first thing you have to do is to what put your functional group. Let's assume this is what an aldose, that is aldoses. Okay, the functional group will be at the what at the end of the chain here, and hydrogen. And after this, after putting your functional group, close your what your chain at the bottom and close it at the top. That is, put something at the bottom and put something at the top. What do you think you are going to put at the bottom? It is OH, hydroxide, because after the functional group, the like for the definition of carbohydrates, after the functional group, the rest of the carbon will be filled with what OH. So the functional group is here, so just put OH at the bottom to cover the chain. So I don't need to put anything at the top again. The functional group has already what covered the chain. Now let's assume it is what all these ketones. You know, ketones, they don't have their functional group at the this thing at the terminal end. They have their functional group somewhere in between the chain. So let's assume we have this 4, 1 2 3 4 5. So you know, for ketones, their functional group will be on the second carbon. Now then close the chain. It means that what at this bottom here you are going to put what OH to close the chain, and hydrogen. But this top is still open. The functional group did not cover the chain at the top, so you have to cover the chain at the top with what OH and H. Then you are going to fill your OH using these letters. So for the E, which are the what erythrols, okay, what are we going to do? Erythrols is what an alkana. So we are going to put the functional group first and cover it at the bottom. Okay, so we've already covered it at the bottom. The chain is covered now, and you are going to write your letter E, which means that what the OH are on the what right, OH and OH. So hydrogen here, hydrogen here. So this is the structure of what erythrols. Now for the structure of erythrolos, erythrolos is what a ketose. So don't forget that what ketones have their functional group somewhere in between. Ketose is just like when we say kissing, so you don't kiss outside, you kiss somewhere what in between. You try to what hide when you kiss, okay? So they don't kiss on the what terminal carbon. So the first thing we have to do is that what put your functional group, then close the chain at the bottom. We've already closed it at the bottom, but the functional group did not what close it at the top. So you have to like put something at the top to close your what chain. And we are going to write letter E, meaning that what your OH will be on the what right. So let us add the OH. This is the only OH left. So you put your what hydrogen to what complete it. So this is the structure of what erythrolos. The next one is ribose. It means that what all our OH is what going to the what right. Put the functional group first. It is what an alkana. So this is the functional group. Close the chain at the bottom. This is the chain being closed at the bottom. Then fill all the OH on the what right, because the R is going to the right. So I have it as OH, OH, and OH. Then hydrogen will be here, hydrogen will be here, hydrogen will be here. Now for the next one, this is what ribulose. Ribulose is what a ketose. So put the functional group on the second carbon, close your chain at the bottom, okay? But the functional group is not closing the chain at the top, okay? So you have to like put OH at the top to close the chain. And it is also right, so all the OH will be on the what right hand side. So OH, OH, and you put hydrogen here and hydrogen here. I hope you understand why we did not put anything here. The bond around the carbon is completed. So 1 2 3 4. I hope that is clear. Now for the deoxyribose, deoxyribose is also what ribose, but the only difference between them is that what in deoxyribose, oxygen has been what removed from where the first chiral carbon. It means that what all the OH will be on the what right hand side. So OH here, OH, OH. But because this is the first chiral carbon, the oxygen has been removed. Instead of having OH, we just have hydrogen and hydrogen. I hope that is clear. So this is the structure of deoxyribose. The next one is the structure of arabinose. Okay, so how do we draw arabinose? The R, that red vertical line will be the what carbon chain. This one is telling us that what put all the OH on the what right hand side, and this A is telling us that what we have one OH on the what left hand side, and because A is the what first letter, so the OH will be on the what first chiral carbon. So let us fill. So close your chain, put your functional group, close the chain at the bottom. Okay, now our functional group for alkane has already closed the chain at the top also, so we don't have to schedule ourselves. Just put your OH, and OH. But for this first chiral carbon, we have A, so the OH will be on the left. And fill all this one with hydrogen, hydrogen, hydrogen. So this is what arabinose. Arabinose. What about the other guy? Lysose. You are just going to write letter L, which is this letter L. Can you see where I got my letter L? So we have OH here. Okay. OH here and OH here. You can see the way the OH forms letter L. Can you see it? So that is the lysose. So now the next thing now for us to do is to what? We are done with the real. Let us come to others. Others, that is, it's glucose, galactose, fructose, etc. Anything apart from the real, they follow this law. And what is the law? Others follow the triangular law of what? AB tutorials. Okay? Probably like we're going to see the triangular law now. So e.g., we have the glucose, xylose, galactose, fructose, mannose, etc. So where is it? Let us draw for glucose first. We have glucose first here, so we are going to draw the structure of glucose. Don't forget that what your glucose has how many carbon? 6 carbons, right? So draw your 6 carbons first. 1, 2, 3, 4, 5, 6. Then put your functional group. Close the chain at the bottom. I hope that is clear. So you are going to fill your what? OH using what? Triangular law. And what is the triangular law? You are going to start forming your triangle from the right. So you put something here, you will put something here, and you will put something here. You will notice that what this has already formed a what? A triangle. Okay? So this is what? A triangle. So that is how you are going to fill your OH. So you are going to put one OH here. So let us clean the triangle now. So one OH here, right, on the left, and another OH here. Now we are left with one OH here. You are just going to put it on the what right hand side, because all the O structures we are drawing here is what? Structure of the carbohydrates. And we said the last chiral carbon that we determine the type of glucose or the type of carbohydrate. So this is what a D carbohydrate. So fill here with H, fill here with H, fill here with H, fill here with H. Now the next one is the structure of xylose. Xylose is part of the what? 5 carbons. Okay. So the first thing, put the functional group first. And don't forget that what xylose is what? An alkane. So alkane, we have its functional group at the end of the chain. Put the functional group, close it at the bottom. The functional group has already closed it at the top, so you don't have to stress yourself again. Just fill your OH using what? Triangular law. Okay. This is the triangle OH, OH, and OH. So OH here, OH here, and OH here. So we have hydrogen here, hydrogen here, hydrogen here. So this is what the structure of xylose. I hope that is clear. So now this galactose. Galactose also has how many carbon? 6 carbon. And galactose is also a what? An aldose. Okay. So put the functional group here. Close your chain at the bottom. Then start filling. Follow your triangular law. OH here, OH here, and OH here. Right. That is what we are supposed to have it as what? Let's form our triangle here. But no, galactose will not do that. Galactose will what? Betray us. So galactose is not going to complete the what? Triangle. Galactose will not what? Complete the triangle. And there's a reason for that. So there's just we are just going to use a logic here. Now, what is happening? Why do you think galactose did not complete the triangle? So we have OH here, OH here. So instead of galactose, should just put the what OH here, so that we are going to have our what triangle. Galactose will not do that. Do you know why? Galactose betrayed us because someone gave galactose what a gala. Gala is one of the what sausage rule. Okay, so the reason why galactose did not form the triangle was because he has been given a what gala, which is what a sausage roll. So it means that what, instead of the galactose to put the OH here, it will not put the OH here. It will then put it what here. Galactose just completes the this thing for us. No, can you say did not form the triangle? Okay, and this last chiral carbon, what do you think the last chiral carbon will determine? The type of carbohydrate, which is what this. So you put the last OH on the what right hand side. I hope that is clear. So you put hydrogen here, you put hydrogen here, you put hydrogen here, hydrogen here. I hope that is clear. So that's the structure of galactose. So the next one is the structure of our what? Fructose. So do you think fructose is going to betray us or not? Like the way galactose did? Yes, fructose also will betray us. Why? The guy will be giving a what? A fruit. So the guy will be like, I'm so sorry. I've been given a fruit. I just have to like I can't complete the triangle. Someone has given me a fruit. So the guy will not complete the what? The triangle. Do you understand that? And also don't forget that what fructose is one of the what ketose. Don't forget that what ketose is just like saying kissing. So they don't have their functional group outside. That is, they don't have their functional group at the end of the chain. They kiss inside, okay? So they kiss on the second carbon. So they try to cover themselves. Okay. So always remember the fructose is sweet, the same thing as the what the kissing is sweet. Okay. So the first thing you have to do is what? Draw your six carbon structure. 1, 2, 3, 4, 5, 6. Your functional group on carbon 2. This is it. Cover the chain at the bottom. This is it. Because the functional group did not cover the chain at the top, put your words cover at the top also. I hope that is clear and you understand why. And we are going to fill. That is form our triangle. So, but no on a non, we do start our triangle from the what right and on the what second carbon. Look at this right. Look at this one on the right and second carbon, right and second carbon, right and second carbon. But the second carbon has occupied the position. I mean, this functional group has occupied the position where we are supposed to start forming our what our triangle form. It means that what we have to come down to this what third carbon and start forming our what triangle. But because we've come down to another carbon, we will not start the triangle from the what right. We are going to start from the what left. So let us form our triangle. So triangle, triangle, triangle. This is the triangle. But no, fructose has been bribed with a what? A fruit. It will not form the triangle. So we have the what? The last OH to be here. So we have OH, OH, and OH, and that's all. There is no any other carbon that is not filled. Hydrogen, hydrogen, hydrogen. So this is the structure of your what? Fructose. I hope that is clear. Now the next one here is the structure of our mannose. From the name man nose, it has NNO. NNO, which can be written as no and no. That is, which can be written as two no. Okay, which is no and no. This no means that what this guy did what two wrong things. No from the word manus. No, it means that what this guy did two wrong things. What are the two wrong things? He started forming his triangle from the what left. The other wrong thing he did is that what he put another what OH on the left again. So these are the two wrong things. No, don't do that. But the guy has done it already. One OH on the left, another OH on the left again. So what do you think the guy will do? He have to what? Correct his two wrong deed with what? Two right deed. Okay? So he's going to put two OH on the what? Right back. So this guy has corrected his two wrong deed with two good deed. I hope that is clear. So you put your hydrogen here, hydrogen here, hydrogen here, hydrogen, and this is the structure of our what? Mannose. So that is the end of the what? Mannose. So you can always watch my video on what how to draw the what ring structure of our monosaccharide and the ring structure of disaccharide. So don't forget to like, comment, and share. Thank you. Cut.